Hi everyone, today I'm going to help you understand the basic aircraft parts, concepts, airfoils, and how you measure their speed depending on what it is. So it's just like flight principles. So we got 5 building blocks of an aircraft, what they are made of. We got the wing, and that speaks for itself. We all know what the wing is. We got the fuselage. So when you think of an airplane, you know when you're going to travel, everyone they sit in their seats, and all of this is in the fuselage. It's the longest part. Here's an airplane. You see this from here to here is the fuselage, and these right now I'm going to explain to you what these are. It's different. You got different parts. You got wings, and then this long thing here is a fuselage. Okay, then we have the tailplane. Now the tailplane is a horizontal stabilizer which provides pitch stability. We're going to explain what pitch is, yaw, and roll. Okay, so pitch is the angle at which the airplane can go up and down. So the tailplane helps to stabilize it, and we call it the horizontal stabilizer. And we got the fins, and the fins, they are the vertical stabilizers. They help with the yaw. Now what the yaw is, if this is the pitch, right, the yaw is going the direction, changing the direction of an airplane this way. We call it the vertical stabilizer. And now obviously we have engine, which generates the thrust, right? Now, so now we have another thing, which is the four surfaces. Now the four surfaces, right? They are like when we talked about the four parts, the tailplane and blah blah blah. These are the surfaces on top of these things. So we got the flaps, okay? The flaps, so they are like the trailing edge of the main wing. You've got the wing here, okay? So let's go back to this. I love using this airplane. We got the wings here, right? So the trailing edge, that means the end of the wing here, so that's where you get flaps. And then I'm going to show you a real life picture of it soon. And it increases the lift at low speeds so that you do not need to use a lot of fuel to put on the lift, right? You could do it at lower speeds. We got elevators. So they are the movable parts of a tailplane. So we talked about tailplanes and they control the pitch. That's what an elevator does. It's a surface part of the tailplane. You got the ailerons. They're also part of the wing. Okay, it's also near the trailing edge, but it looks different to the flaps. I'll show you the picture. You'll understand more from what I'm saying. And so what they do is like they move opposite ways to control the roll. Roll is rolling the aircraft, right? So we have two wings, okay? We got a wing this way, a wing that way. We got ailerons here, ailerons here. Now, if this aileron goes downwards, this aileron goes upwards, then it will roll this way. So this is what ailerons do. Then you got rudder. What a rudder does is that it's also at the trailing edge, but off the fin, and it controls the yaw, because we said the yaw is controlled by the fin, and we said the pitch is controlled by the tailplane. So the surfaces on top of them, they also have names, elevator and rudder, okay? So this is something we have to remember. Control is achieved by changing the lift on the relevant surface. So we have these four surfaces. When we change the lift on each different surface, it does a different thing, okay? It creates a moment. It's that moment force that allows about the appropriate axis that allows either the pitch, the roll, or the yaw to change. Right, so this is the picture, and you could see now very well. I would leave it for a bit. If you want, you can pause the video so you could have a better look at it. You could also search it up like a diagram and you can understand it more. As you see here, the wings, under the wings you got the ailerons, and then you got the flaps, they're near each other. You got the fuselage, you could see the wings, that's not tough. And these two things, the fin and the tailplane. So for me to explain to you more, we're gonna use this, right? Oh, sorry. You see this aircraft. You see the horizontal thing coming out of here, right? That is the tailplane. The one up is a fin. Okay, think about fins in, I don't know if this can help, but in fish. So yeah, and then you got the surfaces on each of the tailplane and elevator, as you could see. I mean, yeah. Right, now we have talked about the axis system, right? We have talked about yaw, pitch, and roll. We're going now to dive deeper into it. So we have something called reference frames, and this actually is a bit difficult to understand. You will understand what I mean. So when the aircraft moves and rotates, the reference frames also move around. So we have the common and simple conventions, which is, this is simplified by the way. The x-axis, which is aligned to the fuselage pointing towards the nose. You could see from the picture here I created. Well, not really. And then the y is aligned to the right wing. Okay, so think about, like, just put yourself right that way. You could see some the and then you get the z-axis, which is pointing downwards. Now, because I obviously can't draw a 3D aircraft, I tried my best, and you could just imagine that, right? Yeah, points downwards, so it completes a right frame, just like, 3D graphs. 2D has x and y, 3D has x, y, and z. This is how we think about it, and each axis is 3D perpendicular to the other. So always remember, the x-axis goes along the fuselage to the pointing nose. Okay, the y-axis is aligned to the right wing, and then you have the z-axis going downwards. Okay, now the altitude in the orientation of body fixed frame relative to an external reference frame that does not rotate with the aircraft. So these are body fixed axis system. It will not rotate with the aircraft. Okay, that's one of the things to understand. It's usually used to like for pilots to understand how they're going to navigate. Now, yay, our favorite one, roll, pitch, and yaw. Some people, and that was me before as well, have problems with remembering what is yaw, what is pitch, what is roll. Now, this is my aircraft again, right? So this is my aircraft. I'll do this so you could see from this point of view. When we're saying it's rolling, roll, roll like this. Think of this. Pen. It's rolling, right? Roll, we all know what rolling is. Just think of it that way. Roll. Okay. Now what pitch is, so think about pitch is something that goes up, right? So pitch, and then it could also go down. That's still a pitch. Yaw is the only one where, like, I can't remember, so it's just the left one out, so it's this way. Okay, so for roll, now this is the part where it's tough to remember. Roll, okay, is rotation about the longitudinal x-axis. Remember what we said the x-axis is? Through the fuselage to the nose, right? So it is rolling like on that, like relevant to that direction. Okay, It's also controlled by the ailerons, which we already talked about, remember, if you remember that. And this is very important to remember actually. A positive roll will lower the right wing, also called the bank angle. We will talk about banked angles later, don't worry. So pitch is rotation about the lateral y-axis, okay? So y-axis was the one that goes towards the right wing, okay? So it is that way, okay? Let me show you, like this, okay? So it is going in the reference to that axis and is controlled by elevators, right? So a positive pitch rotation pushes the nose up, okay? Then you got the yaw, and the last thing you remember, we talked about x and y, z is left, so then there's no other choice than z. So that's how you remember, okay? Use these techniques and it's controlled by the rudder, okay? So roll, aileron, pitch, elevator because it elevates up and down, pitch, okay? And then yaw is the rudder, okay? Now, we got these four forces of flight, and this should be very simple. If you don't understand this, then maybe you have to, it's fine. You should just, I can tell you right now what it is. So you got an aircraft, right? And you got the weight. Every object has a force that goes downwards, which is the weight. And that is mass times the gravitational whatever, gravity. Then you got the lift. Lift is upwards. Something that goes upwards is lift, okay? Thrust is what makes the aircraft go forward. And drag is the resistive force of thrust that keeps it to that side, okay? Now thrust is generated by the engine, lift is generated by the wings, weight is just, you know, the aircraft's mass times gravity, and then drag is what we said. Okay, I don't want to stay on this too long. Right. Oh, this is very important. When it comes to aerospace engineering or like understanding how aircrafts work, we need to understand the anatomy of an airfoil. The anatomy of an airfoil here, remember an airfoil is, so you see this, the wings. You cut the wings and the cross section is the airfoil, okay? So we have four important things to remember of the anatomy, and I have, as you could see, I have labeled them for you, okay? We have the chord line. That is a straight line between leading edge and trailing edge. So from the pointy part here to the pointy part here, that's the chord line, okay? The chord is the length of the chord line. So if you have the chord line, what is the chord? It's just the measurement of it, okay? Just keep it simple. Don't think way too much about it. Camber line is different. Camber line, so it is a line that always is midway between upper and lower surfaces. Think about it this way. It's like kind of symmetrical, but not obviously. Airfoils are not always symmetrical. But yeah, it's like it's curved to look in that way, if you understand what I mean. And then we have the cambers. So here, I know my video is covering up the notes for camber, but I would tell you what it is. So it's like the maximum distance, okay, which is like it's like found anywhere between the leading edge. So remember what the leading, you could tell. I put it on the diagram. The leading edge and the trailing edge, okay, that's the maximum distance we can find anywhere, okay. And then by convention, what it does is it is expressed as a percentage of the chord, okay. So the chord is the length, okay, from the leading edge to the trailing edge. But if we get camber, it is the maximum distance you can get, so not straight like the cord, maximum distance you can get from the leading edge to the trailing edge. Okay, so it is like expressed as a percentage of the cord. So a camber of 2% means the maximum camber distance equals 2% of the cord length. Okay, so now there's something called NACA, which so you know NASA, right? Before it had a different name called NACA. They created this system for the proportions and ratios of airfoils. Now, not many people use it anymore now, not many engineers, but it's very important to know, okay? So we get different actually structures. We get the 4-digit, we get the 5-digit, we get the series 1, series 2, so many of them. You could check them, search them up, but you don't need to know all of them. It's just good to remember them. I bet you learn it in university or whatever you're doing right now. So NACA describes the airfoils analytically via a mean line, okay, and a thickness distribution along it. So for example, we have NACA with the numbers 2412. So what does it mean by 2412? So 2, okay, is the maximum camber, 2% of the cord. 4 is the camber located at 40% of the cord. And then 12 here is the maximum thickness, so 12% of the cord. They're all percentages. That's why cord is very important to know the length of the cord, because it's used to describe the airfoil properly. Okay, so we have different ones. Now the most important one to not important, but it's nice to remember, is the NACA 0012, which is the best known 4-digit airfoil. It is completely symmetrical, so the camber is actually 0. Okay, as you could see here, because you got the two like first numbers are zeros. That is because the camber is 0. Okay, so the maximum camber percentage is not going to be 2%, it's going to be 0% because they don't exist, with 12% maximum thickness. And yeah, so next. Now, this is going to be a long video, I'm really sorry. Right, so now we have to describe the wing in plane view, right? Now we described the parts of a plane, we described the airfoil, the structure, but what about the full plane, right? So now we got different terminologies we have to remember, okay? So the root and the tip describe the plane's wings, okay? So the root is the wing section attached to the fuselage. Now you might think like, oh, it's the closest one to the fuselage, but actually the wing, there is still part of it inside the fuselage, okay? And that is like something to always remember, but the tip is the farthest point from the center, okay? Now the span, and you have to remember, it has a letter or like a, so because it's used, you have so many formulas, so many. Span is the distance from one wingtip to the other. You can see it in the red line there. Then mean chord is the average chord across the span. The reason we're saying average, because airfoil, right? Obviously, airfoil, when you take cross section, it's not the same size as the other cross sections. It increases, it decreases on the tips. So you take all of the chord across the span, you add them and divide them by whatever the number is, you get the mean chord, okay? Then you got the tapering, I don't know how to say it, tapering ratio. So it is the ratio of tip chord to root chord. So instead, mean chord is actually from like tip to tip, mean chord. tapering ratio is from tip to root, okay, chord. Now we have also wing area. That is the area of the wing in top view, as you see that. Just and then we get sweep angle. Now wing angle in the XY plane relative to the fuselage. Okay, we call it the sweep angle. Okay, so wait, let me make you think about this. So if you have the fuselage here, you have X here, Y here. Sometimes it could increase, sometimes it could decrease. Okay, it depends on how the pitch is. Aspect ratio, okay, and wing platforms. Now, you can have different types of wings. Depends what the aircraft is used for. Some aircrafts are for commercial use. Some of them are for like fighter jets, military. And if you're a big fan, you would understand what I mean, right? So aspect ratio is you can calculate it in two different ways. Depends on what variables are given to you in the question. You could do it by dividing the span distance by the mean the mean chord. I think no mean camber line. I think yeah. So mean chord. Okay, so B over mean chord. You could also get it by the span squared divided by the area, wing area. Okay, and then you get the aspect ratio. So high aspect ratio wings are long and slender. Okay, so I think this is a good idea. This is a good way to explain it. You see how long and slender it is. So it has a high aspect ratio. Low aspect ratio are usually short and stubby. Okay, so I've shown you 4 different types. Now there are too many, obviously. You get the rectangular, you get the tapered, swept, and delta. Delta usually you'll find it in military. And yeah, so next. Now, how airflow meets the wing, that is very important, okay? I've made a video about lift and drag, but I didn't get very deep into it because obviously I wanted to keep it different, right? So we are going to talk about the angle of attack, okay? So we have talked about it before, and if you don't know what it is the angle between the airfoil, okay, and the flow stream, okay. And so here you could see alpha is the angle of attack, and to find alpha what we do is the arctan of W over U. W over U is actually like a reference line in the x-axis and z plane, x plane, and the direction of the airflow, because remember it's in 3D, so you have to be careful. You have to use some trig, a lot of trig actually, to find W and U. And then you got the side slip angle. This is different, and this is beta, okay? So the angle between the free stream components in the xy plane and the x-axis. XY plane and the x-axis, okay? So velocity is decomposed along the body axis into u, which is along the x, v along the y, and w along the z. So when we are saying alpha equals arctan w over u means along the z divided by the x, okay? Because you could see we said it's reference line in the xz axis, and for side slip it's xy axis, so therefore it is the v, okay. Now however, to find beta it's different. It's arc sine of v over the square root of u squared plus v squared, so you have to use Pythagoras here, okay. Now we're nearly done. I know the video is a bit long now. So we got the TAS and the dynamic pressure and the EAS. Okay, TAS is the true airspeed. Now you'll be like, well, why is there true airspeed and equivalent airspeed? Because of uh, relativity. Okay, so speed relative to the air, which is not on the ground, is the true airspeed because it's up. But if it's the sea level airspeed, so we'd say not on the ground but sea level airspeed, giving the same dynamic pressure as is called the equivalent airspeed. Now, what dynamic pressure is the pressure associated with the motion of air, and Q equals half rho v squared. I'm not gonna talk about it a lot. It's just a formula you have to remember, and what we sometimes call the EAS, the VE, and you can see the formula here. Just sometimes all you need to do is remember the formulas, okay? And then now we have recap here. Free stream, right? So we've talked about free stream a lot. The air far upstream of an aircraft, okay, before the airflow has been distributed. So we've got the airfoil before it hits the airfoil and distributes up and down the airfoil. That's a free stream, which values use the subscript, which we're gonna use these subscripts later, okay? V infinity, P infinity. They look weird, but it's because we're taking it at an infinite distance from an aircraft, okay? And yeah, so this is all the recap we have done, everything. And thank you so much for listening and watching. Have a very lovely day.